Good afternoon, everybody. Those of you who are at least on the East Coast, good afternoon to you. Good morning to everybody who might be a little farther west of Orono, Maine, or where I am right now, Blue Hill, Maine. Thanks so much for joining us today. I'm John Diamond. I'm the president and CEO of the University of Maine Alumni Association. Our association is an independent organization of over 110,000 members. And our members live in all 50 states, the District of Columbia, and in more than 100 countries. So we're all over the place. And we're glad to have so many of our alums and friends join us today. We're very excited to have Dr. Kimberley Miner sharing her insights and experiences with us regarding one of the most serious and timely topics of the day, climate change. But before we hear from Kimberley, I'd like to introduce Grace Elton. Grace is the CEO of Tower Hill Botanical Garden in Boylston, Massachusetts. And she's been in that position for about 5 years now. And she has really developed a wonderful reputation for being a visionary and a leader. So we're really excited that Tower Hill Botanical Garden has agreed to co-host this very important webinar. So Grace, thank you. I'd like to welcome you and ask you to share any thoughts you would like to before we get started.
Thank you so much, John. As John mentioned, I'm Grace Elton, CEO of Tower Hill Botanic Garden. We are a 171-acre botanical garden in central Massachusetts in Boylston. So pleased to be co-sponsoring this webinar with the University of Maine. And because I know about over 200 of our members should be on the call. So really so excited that so many of our members, and especially our John Green Society members and board, have taken this opportunity to learn about this really relevant topic. If you're close to the garden, then you know that we redid our 5-year strategic plan just about a year ago. And climate change education is very much at the forefront of that plan. We feel that it's such an important topic and so relevant for Tower Hill to be promoting spreading the word about this important topic. And so for those reasons, we're really, really excited to be sponsoring this and to hear from Dr. Miner later. If you've never been to Tower Hill, this is your official invitation. I would love to see more of you that aren't in our current network visit the garden. Right now, we have a wonderful orchid show going on called Prismatic, and it's pairing beautiful prisms and art pieces with the wonderful giant plant family of the orchid family. So we've gotten rave reviews about it so far. It's through the end of March, and you can either buy your tickets online or we're actually allowing walk-ins now as well. So come learn a little bit about orchids, and please visit our website, towerhillbg.org, to learn more about all of our other wonderful programs. We've got youth, adult programs focusing on science, horticulture. We do things like botanical illustration. We have a lot of health and wellness programs like yoga here on site. So a really great mix of things that you can experience here on site as well as virtually. So please come visit Tower Hill. Love to see you all as future members someday. And really looking forward to this lecture. Thank you, John.
Thank you, Grace. I also want to thank one of Grace's colleagues, Teresa Lee, who was Tower Hill's Chief Development Officer. She's a member of UMaine's class of 1987, and she also serves on our board of directors. So we hope to partner again with Tower Hill and with Grace and Teresa on a future webinar or two. So I promised our presenter would start shortly, and that's what we're going to do. Dr. Kimberley Rain Miner. Dr. Miner is a climate scientist with NASA's Jet Propulsion Laboratory in California. She lives in Pasadena, California, where it is 9:04 in the morning, but she has maintained her ties to the University of Maine, particularly the Climate Change Institute, where she's an affiliated researcher. She completed her Ph.D. at UMaine in 2018. We won't go too deeply into her background since we shared a summary in the invitation you received about the about the webinar, but her background is both extensive and impressive. So she's going to share her presentation with us for the first half hour, roughly, of our webinar, and then she'll take your questions. Now, if you'd like to submit a question, you can do so at any time. And here's how you do it. Go to the bottom of your Zoom screen In the middle, you'll see a little comic strip speech bubble there. That's the chat button. And many of you are well familiar with this. If you have a question, just click on that chat button, type in your question and hit the enter or return key, and it'll send it to us, and we'll share the questions, as many as we can, as we go along. So, great. And just so you know, we are recording this, and we'll be making the recording available on demand on our website. We'll share that information with you all in case you'd like to share it with friends or rewatch it. Okay, so let's get started. Dr. Miner, welcome. The screen is all yours.
Thanks so much. Thank you for having me. And I'm delighted that I've been able to see so many people as you all have come in. There's even a little kitty cat in attendance. So I am just so excited to be with you here today and to chat with you a little bit about my time at UMaine, what I've done since, and some of the implications for all of us. So I'm going to go ahead and share my screen. Please give me just a moment as I get set up and move into presentation mode. I'm sure you guys are all old hat at this now. So as John mentioned, let me change one more thing on my screen. There we go. As John mentioned, I am a researcher at the NASA Jet Propulsion Laboratory, which is at the California Institute of Technology, or Caltech, as we often refer to it. I'm also a research assistant professor or a research affiliate at Climate Change Institute and a professor of practice at Virginia Tech. So today I'm going to be going over some of the work that we've been doing recently at Caltech, and then talk to you a little bit about, well, I'll start with how I got there and a little bit about what I was doing at UMaine and how this has led pretty directly into the Caltech work. We just had 2 papers come out in different issues of Nature. So this is a really timely opportunity to go over some of the work that our team has done and what we found in our research. So at UMaine, I got my PhD, just like John was saying. And from there, I went to the Department of Defense. I was working in DC for the 2 years outside of UMaine. Have published a number of papers, both at UMaine with Carl Kreutz. And since I don't have any of our very recent research, except for some little information about the Everest project. So at UMaine, while I was still a PhD student, we did a lot of research in the Arctic. You can see this is our tents on the right-hand side. Mine is the one that's almost a little bit too dug in. And then on the left-hand side, you can see the plane that flew us from the lower lands onto the glacier where it landed. And then we were able to ski out of the airplane. So pretty exciting stuff. Oh. And part of what I was doing at UMaine is understanding the risk to downstream residents from glacial meltwater. Now, I was really interested in this because it's just assumed pretty broadly that glacial meltwater is some of the cleanest on Earth, or at least it was when I started my PhD. And what I found, and a number of researchers have found since, is that there is a potential cancer risk from some of the weird and icky stuff, including DDT, which I'm sure many of you are familiar with, that is trapped in glaciers. And I'm going to get into the mechanisms of that in a little bit, but just a little bit of an overview of what I did at UMaine. I also was very lucky to join Paul Majewski's project on Mount Everest, where he worked with National Geographic. One of my mentees is here on the right. She's just about to finish her PhD at UMaine, Heather Clifford. Absolute powerhouse of a researcher, really, really big deal. So we're expecting incredible things from her. And really enjoyed participating in the Mount Everest project in my capacity as a research professor at UMaine. I'm also an If Then ambassador, and this is a program that was set up by Lyda Hill Philanthropies and AAAS, who run Science Magazine. On the left, you can see a very fun photo shoot we did with representing our sciences through characters from different Disney stories. And on the right is just an interview that I did. So we've had a lot of different opportunities to do outreach to younger people and talking about what science is like and how to be a woman in STEM. So highlighting the importance of females and people who gender identify as female in STEM fields. On the right, this was in a CBS show that we did some kayaking talking about climate change, and then very excited to share the press release went out this week that our statues will be moving to the Smithsonian next month. So if any of you are in DC, we'll be in various Smithsonian museums. I don't know where I'll be just yet, but I'm hoping for the Air and Space Museum. Okay, so that's a little bit of an overview about where I came from. I'm happy to talk more about that. But where I've moved into in the NASA realm is in the Arctic. So we're still looking at what's going on in the Arctic, but not with glaciers this time. We're looking more about permafrost thaw. And I'm going to tell you guys a little bit about why we're interested, what permafrost is, and then some of the nuances that we are picking out and trying to highlight. Part of what I really like to do is look at the lesser known risks or the things that maybe we are taking for granted are not risks, the assumptions we're making as a global community, and just make sure we're questioning them, make sure we don't end up having surprise things that are bad and happening because of climate change. So as I'm sure you all know, the Arctic is changing. This is a picture from pre-pan. Actually, no, I'm sorry, this is 2020, when a huge chunk of one of the ice sheets in Greenland disintegrated. There's also been a number of mentions over many years, this is actually from 2015, of these holes exploding in Siberian Arctic. And it took a little bit of time to figure out what was going on, but it turns out that's from thawing permafrost and from methane trapped in the substrate and then exploding out. As the Arctic is changing, it's becoming right now a little bit more of a wetland dynamic in some places, where all of the ice and embedded structure of ice and glaciers is melting and becoming this layer of water that's both above and throughout the permafrost. But what we're really interested in is all of the things, again, that people are not talking about. We're talking a lot about the potential for greenhouse gases like methane to release from the Arctic and move into the atmosphere. But I'm also interested in all of the other things that could be released from the permafrost that maybe isn't getting the same level of attention. So let's step back and talk about what permafrost is. So permafrost is soil or detritus, a bunch of different things that has been frozen over 2 years or more. And a lot of it remains from the last ice age. So we're talking about up to 1 million years old, but definitely at least 100,000 years old. And with prior glaciations, ice sheets have moved across the landscape, frozen the soil, started to build permafrost and then moved back. And this has happened over many, many, many years, many generations, many centuries, until you have this very thick layer of frozen soil, detritus, any kind of organisms that were trapped, all of that in this permafrost layer. As I've alluded to, it contains organic carbon, plant and animal detritus, so dead things. And that can lead to carbon release in what we're calling the permafrost carbon feedback. And we'll get a little bit more into how that leads to carbon release in just a second. However, as you know, rapid thaw in the last 50 years is changing the dynamics of the Arctic and releasing greenhouse gases, but also other things that are stuck in the permafrost components. The dynamics and where and when and how this is happening is something that we're really intently researching as a community. A number of my co-authors are strong leaders in this field, but it really depends on the underlying structure. So what is in the permafrost? What's it made of? What the permafrost is made of and the concentration, the density is different in Siberia than it is in Alaska, exactly the same way that the soil in Maine is different than it is in California. So I want to get a little bit more into what is in the permafrost, because this is the subject of a couple different papers, like I mentioned, that we just put out, but it's also an interesting conversation that doesn't get highlighted in the same way. So we were trying to go through all of the literature, all the papers that have been published and all of the scientific literature, and get an understanding of what other folks had seen, what all the other researchers were doing, where the gaps were, and where we need to go next. So this is an image from the Nature Climate Change paper that we just put out, I think it was November or December last year. On the left-hand side, you can see that with gradual thaw, with a little bit of thaw every year, you have a pretty stable permafrost structure. With abrupt thaw, this was something that was discovered and coined by Merit Turetsky, who is a co-author of mine and a professor at the University of Colorado. And the idea basically is that because of the way that climate change is heating the permafrost and a number of different dynamics, including water flow and wildfires, you have the opportunity for a loss of structure very quickly. And that can even create what we call thermocarbs, or basically lakes on top of the permafrost. And what happens is, you can see from this dynamic here, is on the left-hand side, anything trapped in the top few layers of the soil, might come out eventually. But with abrupt thaw, you're already seeing potentially up to 1 million years old of microbes that could come out, because you're seeing more of the layer exposed than if you were just to see gradual thaw. It kind of dropped off the side, as you can see right here. So for example, we've included some illustrations of what could be in these layers, what's been found. This is the name of a microbe that was 700 years old, and that could emerge. Some more microbes that were 30,000 years old, 100,000 years old, and then cells that are still alive, but are really just trying hard to keep themselves alive. And all of these may have the opportunity to emerge because of abrupt climate change. So let's get into a little bit of what these are. Cold adapted generalist microbes with lipid membranes is what we're generally thinking. So what we call extremophiles. The organisms that are really able to keep themselves alive, even though it's really high pressure, it's really cold temperature, because they've got these fat membranes on a very small scale. And they're able to clean up their DNA, reproduce DNA, and find a way to survive even in these really aggressive temperatures. Some of the places that they like to survive are cold methane seeps. So little cracks, if you will, in the permafrost that might be a little bit warmer or a little bit more liquid. Brine lenses, which is exactly what it sounds like, right? So salt water that is trapped in different locations, or other types, salty water, if you will. And in permafrost substrate. So just in this actual material of permafrost, for some reason, with certain mechanisms, they've been able to stay alive for this time. Sounds like we have an open mic. So the other thing that we're interested in is unknown bacteria, viruses, and microbes. As you can see, this is a pretty impressive cross-section that we have of microbial life that we know about. But there's a lot of Arctic. The permafrost covers 1/4 of the land surface. And so there's a strong opportunity for microbes that we are not familiar with that can be up to 1 million years old, what we've termed Methuselah microbes, right? Because they come back from the dead, metaphorically, to emerge and interact with the local ecosystem. So that was something that we're pretty interested in, and one thing that our team is going to be looking at in the future. Now, in more recent human history, anthropogenic or human-derived, human-interacted microbes in the permafrost include the plague, Black Death, smallpox, and unknown viruses. Right around the time the COVID-19 pandemic started, there was a virus found called Alaska pox that went into a woman's system. Not sure the mechanism there, but there are some viruses emergent that we do know about that are really just not that great. One of the weird things is researchers have also found antibiotic resistance in some of the microbes. So these microbes were in the permafrost before antibiotics potentially were discovered and derived, but they, for some reason, have antibiotic resistance already, maybe because they're such, impressive extremophiles. So that's something that we definitely need to keep a handle on and keep watching as this evolves. These are names of antibiotic species that we are not able to use against these microbes. And then other diseases that we consider eradicated in locations where people have been buried in the permafrost, again, because we thought it was going to stay long term. These might have the potential to be emergent, and that does include something like anthrax. All right, so that was kind of a quick rundown of microbes in the permafrost. There's obviously a lot of growth there, a lot of research that needs to be done, but what we know, we covered in the paper, and it's basically a very interesting new way to look at climate change and the potential for old ecosystems to emerge and interact with present ecosystems. Well, in a present ecosystem, one of the things that we have all over the planet, including at the top of Mount Everest, is anthropogenic contamination. So human contamination, our stuff. And on the right, that includes plastic. It can include scuttled Navy machinery, or on the left, you can see that does often include oil spills or chemical dumps. One of the things that I did in my PhD at Maine was look at and talk about how this contamination even gets to the Arctic. So sometimes we drop stuff there, right? Sometimes we leave ships, we leave military bases. I'll get into that. But sometimes it comes from other latitudes. So you have to remember that the Earth is a closed system. Anything that happens on the Earth functionally stays on the Earth, right? So even if we were spraying DDT in Louisiana, where my mom is from, there is a potential for some of it to do what we call the grasshopper effect and hop up to the poles, really move all over the planet. But then because the poles, the North and South Pole, are very cold, the chemicals interact with the snow and interact with the temperatures and can become housed in the glaciers and in the permafrost at the poles. During my PhD, I always made the off-color joke that, this would be a great situation for humans. It's like a faraway garbage dump, except for the fact that the glaciers are melting and the permafrost is thawing. So a lot of the chemicals that we have used over recent history, over human history, have the potential to reemerge from the Arctic and impact people who weren't even using the chemicals, not only because they are younger generations, but also because, they're residents of colder latitudes. So what are we talking about here? One of the things I looked at in my PhD was persistent organic pollutants, POPs. You may have heard of them. It includes things like DDT, hexachlorohexene, which is another pesticide, PCBs, which is an industrial surfactant that is not used anymore, but is all over the place. And our study from my PhD and another study out of Italy showed human risk from biomagnification. So the fish and other organisms in the water uptake the chemicals and it gets stronger in their system, and then they pass it on to the person or organism who eats them. And a study just came out. My husband, also a UMaine grad who works for science, just highlighted a study about chemical mixtures moving from mother to baby in utero. So this is a pretty serious problem of how these chemical mixtures, these persistent organic pollutants, are moving through the ecosystem and into humans. There are some very high concentrations in glacier ice and permafrost of all of these constituents. And it also includes plastics, as I've mentioned, like the microplastics, fragrances, and plasticizers. I reviewed a paper recently, an excellent paper that was coming out, I believe, of Ukraine, talking about how after the Soviet Union fell, there was a strong uptick that you can see in ice cores of people using more plastics, fragrances, and plasticizers as Russia kind of changed the tenor of its consumption. So there's very direct evidence of the ways in which we are contaminating atmospherically all of these frozen places with what we're using even on a day-to-day basis. There have been a few studies of heavy metals, and this is part of what we're going to be focusing on this year with my team. But when we're talking about heavy metals in the Arctic, we're also often talking about open mines. So mine tailings were left, whether it was from the westward push by white settlers or from other types of mining activities that are more recent. Sometimes what's in the Arctic just gets left there, as you can see from the photo on the right. And so with mine tailings, that could include cadmium, nickel, mercury, arsenic, and one open pit mine that was surveyed in the literature has these high concentrations that you can see in the second bullet point. Overall, one of the colleagues and great researchers that I work with estimated that there could be a ton of mercury in the top 3 meters of soil that's now mobilized because permafrost is thawing more rapidly. There's also an estimate from a government agency that bioaccumulation in fish, so fish uptaking heavy metals and then passing it on to other places, could see up to an over 200% increase by 2300. That feels really far away, but basically what it means is that everything would have been mobilized in the water and in the air by 2300 in a way that we're not really seeing right now. Just to really reiterate the bioaccumulation, the glaucous gull species, so gulls, show high levels of a lot of these chemicals, and they transport them from places in the Arctic where maybe there was an open mine to places that are even more remote because they uptake them in their bodies and then release them through their off-gassing and other mechanisms for release. All right, I know we're really in bad news here, so we'll do one more and then we'll talk a little bit about next steps and then we can open it up to questions. This is how I've earned the nickname Dr. Doom, is talking about all these upsetting things. So nuclear waste was our big find for this research paper. It took a lot of digging and we found papers that were literally just Xeroxed and put online from the 80s, 90s, and early 2000s when the research out of Russia that's been at least widely published kind of stopped about the nuclear waste. So what we do know is that between 1955 and 1990, the Soviet Union conducted over 100 nuclear weapons tests in the ocean, air, and lands of the Arctic. There were a ton of different explosive devices, and there's also potential plutonium that got trapped in the sediment, so below the ocean in the Kara and Barents Sea. There's also intentional scuttling of ships. So nuclear ship doesn't work anymore, let's just leave it in the Arctic. And right after this paper came out, actually, Russia sent out a press release. I like to take credit for it, but I'm sure it wasn't us, about how they're starting to clean up some of these ships. But unfortunately, in the most recent drag, in the high seas, they lost one of them. So I like to joke that there's now a trail of nuclear ships from the Arctic all the way down to Moscow where they were taking them and cleaning them up. But the US is not exactly without blame here. One of the things that we talk a lot about is Camp Century, which was an Army Corps location in Greenland. Remember, I just came from the Army Corps, so this is something we talked about at my old job. And basically the base was left without any cleanup, and some snow has accumulated since. There was a recent group that just did a model run looking at when it will emerge from the ice and just, come out into the open. It's not going to be very soon, but there's still a bunch of physical waste, PCBs, sewage, and nuclear waste that's buried at Camp Century. There was also a bomber crash on Greenland. So the point basically is that humans have scattered a bunch of our stuff, our chemicals, our toxins, our metals, all over the Arctic. And as the permafrost starts to thaw, it's releasing more and more of these into the near environment and then potentially into the wider environment. So the concern is that with the thaw of permafrost and the melt of ice, places that have never seen this pulse of chemicals could start to see it. As we've covered, that could include nuclear materials, oils, chemicals, But if you think about the way that some of these chemicals might interact with microbes, there have only been a couple studies going through it. And there could be some very interesting dynamics when you've got very old microbes coming out and interacting with very new human pollutants. The main question that everyone always asks at the end of this lecture is, could Arctic hazards transport globally? As you can see on the left, we've got a beautiful visualization. I like to think it kind of looks like some impressionist painters of how the ocean is moving. Those are the currents. You can see that's you guys there in the Gulf of Maine with the warm water. And part of what we're discussing now is if there's a way through ocean and atmospheric currents for some of these pollutants and microbes to transport globally. Simultaneously, as all this is happening, the Arctic is also greening, which means that there's more vegetation that's able to move in because it's warmer and wetter than it used to be. And, still just a little bit warmer and a little bit wetter. It's not too hot yet, but there's a potential that some of these vegetation and organisms could uptake. They could take up into their systems some of the microbes or some of the contaminants. So it's something that we're very interested in watching, but we really need a lot more information. So with that in mind, a big part of the next steps that we are working on for my project and my mentor's project, which is the Arctic Methane Permafrost Challenge, is looking at these microbes. You can see on the right-hand side, this is the permafrost tunnel that the Army Corps runs in Fairbanks, very, very old permafrost. Looking at the microbes that are contained in permafrost, see if we can get a better understanding of what's going on there. And then also understanding some of the mobility of the pollutants. So we're also going to be working with the University of Alaska Fairbanks researchers on modeling how pollutants and contaminants are moving through the permafrost system. When you add a little bit of water, when you add a lot of water, when you have a strong slope, when it's flat, and all the different ways that we could potentially forecast and plan for what could be coming out of the system. One of the very cool things that we're working on and that I get a chance to work on because I'm at JPL is working with the Mars team. So the Mars team, as I'm sure most of you know, have a new rover on the planet that landed, goodness, I think last year. And on it is a tool called Sherlock. As you can probably infer, it's a reference to the novels. And we are looking for microbial life. So the same kind of microbial life that we are looking for on Mars could potentially be contained in old permafrost in Alaska, because some of the conditions are similar. There's some permafrost on Mars, there's some permafrost on Earth. Obviously, it's very different dynamics with no atmosphere, but we are using the same tools. So these images here are from a study we're going to publish here in just a very little period. And this is the visible image close up of the permafrost. And then this is the fluorescence. So these are the signatures from microbes that are either still in the permafrost or have moved through the permafrost. Some of the neighbor constituents are things that we look up for, organic materials. So all of this is a very cool and interesting way to explore the permafrost, and also develop an index for how we might be able to explore extraplanetary locations, how we might be able to find life on other planets using Earth as a proxy or as an index. So as I promised John in the beginning, I got a little excited. I think I'm probably under my time here. Oh no, it looks like actually we did quite well. But I'd love to take any questions. I'm happy to chat about concerns, interests that you all have. And thank you so much for the opportunity to speak with you all today.
Thank you so much. A terrific presentation. And we do have some questions we're about to get to. Just a reminder, if you have questions that you'd like to pose, please use the chat button at the bottom of your Zoom screen and just type them in and we will get to them. All right. For starters, could you talk a little bit more, educate us more about permafrost? How deep is it found? How far does it extend? I know it's going to change in different regions, but can you give us a sense of how deep it is generally?
Sure. And like you said, it really does matter on the region. Like I mentioned, it does cover a quarter of the Earth's terrestrial surface. And it can be meters deep in some locations, lots of feet deep. And depending on where it is, depending on if it's on the coast, depending on if it's on the inland, there could be more or less decay and thaw throughout the permafrost layers.
Somebody asked the question about is there enough known, forgive me, I'm trying to read it here. Is there enough known about the pollutants that you've identified and are being identified to argue for a faster cleanup?
Yes, definitely. Especially when we start to think about chemical mixtures, which is a very emergent field right now. So what we have with the EPA is we have an understanding of the toxicology and the concerns about one chemical by itself. And when you start to look at what's actually going on in the environment, it's a bunch of chemicals all coming together because that's, things are not separate in the environment. And so then we start to get a better understanding of the toxicological profile of multiple chemicals. And it's starting to look more and more serious. So I would definitely argue that we know enough to facilitate rapid cleanup. It's going to be hard to do. We're going to have to figure out how to do rapid cleanup. In New York, they've tried very hard to clean up the Hudson from the PCBs that were dumped there. And what it takes is basically, giant ships with giant scoops dredging the Hudson. And then where are we going to move all of that soil? We have to store it somewhere else. These things don't decay. So it's a very serious issue. It's a very serious problem. And I think we're just starting to understand the scope of how serious it is.
Thank you. I had a question asking about the drug-resistant organisms that you were talking about. The question is, are these organisms multiple drug resistant, or are they just, as research found them to be resistant to one particular or only one particular drug?
Yeah, very good question. It depends on the organism. So some, are resistant to a number of antibiotics. Some are resistant to, the ones that they have been tested against. There's also, potential testing bias where people can't get every single antibiotic in the world into their lab. So, it's difficult for them to understand, the cross-section of every antibiotic, but the ones that are most used by humans are the ones that are most frequently tested.
Question about the dimensions of the Arctic permafrost. How does it compare to, say, the size of the U.S. or a particular state? Can you put it in some relevant terms there, or describe it in a relevant way?
Probably not more than I already have. I'd have to do some research. So if you think it's a quarter of the land surface, so that's the US plus all the other continents. So a quarter of that is covered in permafrost. I don't know the relative size of the US, which is, really not considerably that big. You can fit the US easily inside of Africa, for example. Yeah, I am not able to answer that question more comprehensively.
That's fine. Thank you. A couple of questions about your experience on Mount Everest and the work you've done there. Could you talk a little bit about that? Obviously, there was a lot of significant research that came out and a lot of buzz about it in the media. Want to elaborate on that?
Sure. So I was not able to go to Mount Everest. I was in the military at the time, so I was not released to be able to do that. Heather Clifford, who I mentioned, who was just about to get her PhD, and Mario Pataki, who is a PhD candidate. They were really the leads with Paul Majewski on that field team, and did a ton of the in-person research. Mario was responsible for getting the samples at the top of Mount Everest that led to all of this great new information about microplastics and PFAS from the top. And then Heather Clifford was responsible for getting all the other samples from the base camp area. So, full credit goes to them for being on the mountain. It was a really bad flu season, even before COVID that year. There was also, those long lines to the summit that you saw in the National Geographic and in other news sources. So it was a very dangerous year. The field team did an incredible job. So, full credit goes to them. I was able to apply a lot of the methods that I had learned and a lot of the relationships that I had. So I led the pollution research, but unfortunately I had to do it from afar. And I used WhatsApp to talk to Heather every single day on base camp, which is pretty cool that we now have the technology to be able to do that.
Just like Sir Edmund Hillary did back in the early 50s, right? Just kidding.
I was going to say, I'm not familiar with that story, how he used his iPhone to talk to everyone in the 50s.
Not quite. Can you, while we're on the topic of the Everest expedition, can you talk a little bit about the Climate Change Institute at UMaine and its standing internationally? Because a lot of folks, especially the folks from the University of Maine Alumni Association, may not be as familiar with its international reputation.
Yeah, of course. So I came to UMaine from Columbia, where I got my master's degree because of the Climate Change Institute. So as you know, UMaine just got R1 status, so that's really good. But even when we were sitting at R2 trying to graduate a bunch new PhD students in order to get R1 back, the Climate Change Institute the whole time has been a leader in research, particularly in colder regions, because we have that great placement in Maine and the access to the Arctic. We've been a leader in ice core research. We have a device, a laser to look at ice cores in a way that we invented. That's been a huge asset to the field. We have scientists that have traveled by boat to the Falkland Islands. We have people who have gone to, including myself, to Antarctica. People have gone to the far north. And we are on the cutting edge of climate change research over and over and over again. I even saw the Climate Reanalyzer, which was created by Sean Burkle and Paul Majewski. It's a way to visualize climate change on the planet and departure from normal. And that was highlighted by NOAA recently as their main suggestion for how to view climate change and all the different dynamics that are going on. So the CCI is a very, very big deal. It has maintained its reputation over its 50 years, which our 50 year, this is our 50 year, we're having a celebration in November. So I'm hopefully gonna go in person to UMaine to give a lecture and to celebrate that with everybody. But it's one of the things that I think UMaine should be most proud of. They also really prioritize fieldwork. So all the students that come through are very, very strongly encouraged to do on the ground work in these remote and interesting environments. And that's why I went to UMaine and that's why I stayed. And, as you've mentioned, I'm still staying. I'm still involved with the Climate Change Institute because I love these people. I love this research and I couldn't leave it.
That's perfect. Glad to hear that. We have a question about the organisms that are being released from the permafrost thaw. Question asks, do you have a sense of the survivability rate in the new ecosystem that they are now exposed to? And what is the projections about what's ahead for that in terms of the consequences of it?
So I'm not sure who asked that question, but you hit the nose completely on the head. So that is the question. So these microorganisms that could be up to 1 million years old, how are they going to deal with a completely different ecosystem? Not a great example, but if you think about, the Jurassic Park movies, how are the T-Rex from the first movie, how is he going to deal with a goat tied up on a pole? How is that going to, how are the microorganisms, not T-Rex size, going to interact with a completely novel ecosystem, one that's changing, right? So we don't even know necessarily where these ecosystems are going to end up when we find another steady state. And we have all of these new constituents emerging. So this is the question. And it's a big part of the work that I'm interested in doing and that we're hoping to do this year as soon as we can get back out into the field.
Terrific.
Great question. That was awesome.
questions about what is being done at the governmental level in terms of Congress recognizing what the issue is. I'm talking primarily about the United States here, about Congress's sensitivity to this and action that is being discussed there, the role that you and other scientists might be playing in advising policymakers about what's ahead and what needs to be done. Could you talk a little bit about that?
So while I do really strongly support the interaction of science and policy, I'm not a policy expert, so I can share my personal opinion on this. This is an emergent topic. We just published this review and got, a ton of press about it. It was in the BBC, it was in the Hill. So hopefully that is something that people are tracking. I, again, personally think that some of Maine senators do an awesome job interacting and talking about the Arctic, including with the Climate Change Institute research, in their pocket. So I think that, as much as they can, the Maine senators are representing, our new research and trying to get that information into their heads. But otherwise, I wouldn't say that this is a very well-discussed topic. There's a lot of things going on right now. I'm sure you all noticed a lot of not great things. So yeah, I think it's a challenge to get some of this information to policymakers when they've got so many balls in the air at the same time.
There was a somewhat related question when you were talking about the military's interest in work in this, especially you talked about the tunnel. Can you explain why the military is interested in the issue of climate change and the work that's being done in terms of what's happening in the areas that you're working in?
So I guess there's two parts to that question. So the first part is about the permafrost tunnel and about maybe Camp Century. So the Army Corps has always been tasked with understanding the ways that humans need to interact with their environment, including an infrastructure, protecting the forces. And so the Cold Regions Research and Engineering Lab, CREL, is the cold section of the Army Corps that is responsible for the tunnel, and I believe was also the progenitor of Camp Century, but I might be mistaken on that. So that's part of their tasking, is to understand how to interact in these cold environments. I think the reasons are obvious now that we're talking about potential conflict in Ukraine, where they do have a different ecosystem than we have in the US. As far as the military's interest in climate change, I was hired to do climate change work by the DoD, and then that was kind of waylaid for a little bit. And then, as I'm sure you saw, the Army just put out their new climate change plan 2 days ago. So it's this national security threat in a bunch of different ways, including threats to food and water, threats to coastlines, not even starting to address the potential human health risks from these contaminants moving through the environment and into our water and food sources. So there's a lot of reasons that the military believes that this is a national security priority. Securing the Arctic has always been a national security priority, but now that the sea ice is really melting, especially on a year-over-year timescale, we have an open ocean where there was, it was locked. So that is something that we're considering in many different avenues, because that gives us a little bit more direct and concrete interaction with China, Russia, Europe, and obviously, our neighbor Canada. They have ocean access as well.
You might have mentioned this, I think in passing, the role of our congressional delegation, but somebody noted that Senator King is the co-chair of the Senate Arctic Caucus, along with Senator Murkowski of Alaska. So,
correct. Yeah, Angus King is also, we really like him in our family. When my husband was in school, right outside of Augusta. In fourth grade, Angus King called him a smart boy. So every time Angus King comes up, my husband reminds, my fully grown, almost 40-year-old husband reminds me that Angus King called him a smart boy. So yeah, big fans.
That's good. A question came in about the more about the microorganisms that are being released, and can you talk more about the ways or the whether they're being transported to other parts of the earth? What is known at this point about how they're being transmitted or transported?
So very little. That's what I was saying in the lecture, is that we really don't know very much. That's part of what our modeling effort is going to do, that we're going to be working on this summer. I do go through in paper, I'm happy to share that as well, the different mechanisms for moving things. And that does include humans, right? So people who are in the Arctic and then coming back down to the lower latitudes, like myself, you know, needing to be very careful about how they transport things. But then you've also got atmospheric and ocean potential mobilization, and also freshwater, right? So you've got freshwater moving across the landscape now in a new way, and then potentially coming to lower latitudes. So there's a lot of different mechanisms that could be potentially mobilizing microbes, but to get a better understanding of whether or not that's a real concern, we are gonna have to do a lot of modeling, and that's what we're starting to work on.
We've got a question about the flooding projections that most recently came out, and do those include the effects of methane release, or was that part of the assessment?
Okay, I can't say 100%. I would highly doubt it. The permafrost carbon feedback, right, is what we call methane release, warming up the atmosphere, releasing more permafrost methane, this circle, right? That's why it's a feedback. We're really trying to understand the where, whens, hows of that feedback. And we don't have a good understanding enough that I think that people are comfortable using it, especially in government reports about the future. So I'm sure they just used trajectories of current emissions and future emissions. The other thing to think about is it's kind of like, I also say this in my lectures about climate change, which we didn't cover today. It's kind of like a snowball rolling downhill. So, you know, by the time we stop the snowball, if we were to all stop using carbon tomorrow, right? Think early 2020, we were to all stop doing anything tomorrow, we would still have a lag of warming and all the different ways in the which the ecosystem has changed over time, still moving forward. So there's going to be a lot of catch up, even if we stopped right today. So I guess all of that is to say that this is the best effort modeling. You know, it really set the timeline back. The report said that sea level rise will rise a foot by 2030, I believe. And then the other thing that I mentioned on the social medias that's important to think about is you have to think about inundation. All right. So it rises a foot, but then you have to think about where that is in as far as the land. So it may actually go further than 1 foot, for example, in the land. And there's a couple different really cool modeling tools that you can, maybe cool is not the right word. There are some informative modeling tools online, and you can see how the water will move into your area, you know, which could be a good thing to do if you live on MDI, Mount Desert Island, or, you know, you live down on some of the coasts, even Belfast, you know, might be worth kind of looking at and seeing how the water might move into your area.
Excuse me, I'm scrolling back. There was a question that was related to that. In terms of all the melting that is projected in the impact on the salinity of the ocean, how long does it take for the level of melting that's occurring now to really disrupt the existing ecosystem? I know it's being disrupted now. I'm trying to summarize this question.
No, you guys are so well informed. That's why I'm chuckling. Okay, so part of what the Climate Change Institute does is look at paleoclimate. Okay, so really, really old climate. That's why we use ice cores. That's why we use sediment cores, tree rings. There is some indication that the ocean may have had less overturning, so like fewer currents, and more of different layers in the super, super, super far distant past, think way before humans. So there is a potential that when we get more fresh water into the ocean, that there starts to be a little bit more of the separation and a little bit less of the overturning as temperatures shift and salinity shifts. You know, even as I'm saying it, it's clear that it could be the other way as temperatures try to normalize and salinity starts to normalize. But that's kind of the concern when people talk about the ocean current slowing down. There is a concern that we're not entirely clear what will happen with these huge melt events for the ice sheets and for the glaciers that are near ocean. If all of this fresh water moves into the ocean, we're not entirely sure if that will impact the currents. It very clearly impacts the near ocean life, that's used to a certain salinity, it's used to a certain pH. So there's a lot of things going on in the ocean right now that are really not ideal. As far as our study goes, there was a microbe species that moved from the terrestrial, from the land into the ocean, and was able to help ocean species adapt to uptaking carbon more readily. So they were able to genetically change the microbial ocean species through, interaction with them and through, combination. So there's a lot of dynamics up in the air right now. There's a lot of things that are changing quickly, and us handful of scientists that are working in this field, kind of scraping together to do work as fast as we can. And then you think you're locked in your house for 2 years. So there's a little bit of catch up that has to happen now too.
Somebody asked the question: how can we access the modeling tools to look at sea level rise over time? Are there public resources there that people can check out for themselves?
Yeah, I can tell you off the top of my head, and then John, I'm happy to send you links to a bunch of the things I've mentioned today, guys. Climate Central is the one I was looking at yesterday. I believe they're a nonprofit. They are not, I don't think, government funded. I'm not entirely sure actually, but they use the NOAA projections, the NOAA maps, and it looked like a good resource to me. I haven't spent too much time on the page. NOAA and NASA, we just put out a new sea level rise tool. It's not so great on the visualizations. It has little dots along the coastline that you have to click on, and then it gives you information for that location. The reason I liked the Climate Central one is it's got this map layout and just turns blue if there's ocean. So it's very clear what's happening. But, NASA does a great job. So the NASA NOAA tool also was just released a couple days ago.
Excellent. Good. Final question for you. You referred to yourself earlier as, or saying others refer to you as Dr. Doom. And so can you talk about, instead of the ocean being half empty, the ocean half full, the glass half full here, given what you know about what's happening, what is happening now that gives you hope that things can be better controlled than they have been up until recently? Are there things underway now that, whether they're policy issues, things that you could talk about, that are showing that there is greater collaboration both within the United States and internationally to address the issues that you've been talking about today?
I have trouble with this question. It comes up a lot because I don't personally think that we're making a lot of progress right now. There's not a lot that gives me hope, and there is a lot that keeps me up at night. I think the way that I usually frame this and the way things that I usually talk about is that I think the younger members of my generation, the millennials and the Gen Z generation, have done an incredible job of starting to advocate for themselves. And even, as very young people, starting to engage with policymakers, with the international media, and voice their concerns about the future. in a way that, I think is really new for a generation to be this engaged with policy this young. So that does give me hope that, a generation, multiple generations of science teachers, of parents, of science communicators have informed two younger generations who are really working very hard to engage with policy. And, being able to talk to you all today, having this large of an audience, this many people interested in the research also gives me hope, because it wasn't so long ago that it was, a couple friends and my advisor showing up to my talks. And it's a huge change in the last few years, how many people are engaged with and interested in climate change. And as you know, in a representative democracy, that's what drives the needle for policy. So I guess that is the hopeful part for me, even though, maybe the COPs have not really moved forward, the collaborative planning on climate change have not moved forward in the way that we've hoped. There is, a groundswell of voices that is coming to bringing these issues to the table. So I think those are the things that give me hope.
Right. Well, this has been a terrific presentation. Thank you so much on both behalf of the Alumni Association and Tower Hill Botanical Garden. Folks, we will be making this video available on demand. It will be posted on the University of Maine's website on our YouTube channel, and we will make sure that the folks at Tower Hill Botanical Garden also have the link so that they can share it as well, and we encourage you to do so. I did put in the chat a link to Dr. Miner's website. So there's a lot of information about her work that you can, and her publications that you can check out there, and I encourage you to do so. So again, Dr. Miner, thank you so much. Thanks again to Grace and Teresa at Tower Hill, to A. Shavir, who was the producer of today's event, and to all of our attendees, thank you for taking the time and showing the interest in learning more about this important topic. Take care, everybody.